I'm Charles Wilson, Staff Product Cybersecurity Architect at Torque Robotics. This presentation will cover an overview of threat model creation. This diagram shows the overall AVCDL training path. If you're taking this training, it's assumed that you've already completed the AVCDL overview training, and additionally, that you've completed the Requirements Taxonomy, Security Requirements, Secure Design Principles, Apply Secure Design, and Threat Prioritization Plan training. Additionally, you should have completed the Threat Modeling Overview training. This training will cover threat model creation. Before getting into threat model creation, let's briefly review where it fits in the overall threat modeling process. Here's the threat modeling process workflow with its 3 individual activities: threat model creation, threat model analysis, and threat candidate triage. Let's consider the threat model creation activity. As the first activity in the threat modeling process, threat model creation is arguably the most important. The system design is considered by the development and threat modeling SMEs. This results in the creation of a threat model. It's important to consider that the system design is not just a singular document. It's anything that can contribute to the creation of the threat model. This includes things like the results of the attack surface analysis, previous threat models, or any other information that the development SME can provide. It's important to note here that the development SME, or SMEs, are not an optional participant in this activity. This is because it's not the place of the threat modeling SME to guess as to the intentions or designs of the development team. The threat modeling SME's purpose here is to facilitate the acquisition of information and to eventually create a representation of the system which is usable for the purposes of threat modeling. If we consider the NIST threat modeling lifecycle, we see that we have diagramming, identification, investigation, mitigation, and validation activities. Threat model creation is represented by the diagram portion of this. That's all we're trying to accomplish here. We're not looking into any deeper meaning behind what the various entities contained within the threat model are. We're merely attempting to identify the constituent parts of the system. This information will be used in the later analysis and triage activities. Here's our idealized DFD. The DFD symbology used has been discussed in the threat modeling overview material. On the left is the resource that we're trying to ensure is secure. On the right is the interactor attempting to access the resource. When we're doing the diagramming, it's useful to show the boundary arcs such that the focus is on the object that we're attempting to secure. Every resource should have a single process that owns it. This is for various reasons, including avoiding race conditions and the simplification of controls. The more processes we have attempting to access a resource, the more complicated both the functional and cybersecurity implementations will be. Rather than using bidirectional arrows for data flows, all data flows are shown unidirectionally. This eliminates any confusion as to what we're discussing when we're talking about a particular data flow. This representation is not without issues. If we were just using this as something to reason on in a non-cybersecurity fashion, it might be sufficient. But let's look at some problems that exist in this particular diagram. The first is that these 2 processes are both named the same, specifically process. This causes issues in that we have no way to distinguish which process it is that we're talking about. Is it the process that's managing the resource or the one that's handling the interactor? A second issue that we have is that in order to make a distinction in communication between the interaction managing process and the resource managing process, we have to put additional notation on the data flow itself. In this case, we can't just say that we have a process-to-process data flow. We have to say process-to-process and also specify that we've got a request. We need to have unambiguous names for the data flows, the resources, the processes, and the boundaries we're using. Because when an issue is created, we want unambiguous places for the development team to look when they're considering the issues. So let's look at a slightly updated version of this diagram. This is roughly the same diagram, but we've given names to the processes which make it very clear what each does. We have the Resource Manager and the Interaction Manager. Now, the fact that they're called managers is arbitrary. We've simply given them unambiguous names. Additionally, all the data flows have been uniquely named in the form source to destination, so that when we're talking about an issue, it's very clear which data flow is being referred to. Now you might be wondering, what if I have multiple protocols being used from source to destination? That's when you would have additional decoration, as seen in the previous diagram, with parentheticals. This allows us to show that a data flow is using a particular protocol. This allows us to disambiguate when using multiple protocols over the same channel. That's enough of the theoretical aspects. Let's now work our way through an example that shows various aspects of how the model creation activity is undertaken. Here's the example system that we've shown in the threat modeling overview training. Let's get into how we're going to translate the system into a DFD suitable for threat modeling. This is the level 1 DFD that was shown in the overview training. And let's look at it in a bit more detail. All the processes shown have been directly translated from the block view. You'll notice that the names are fully unambiguous. We have core service, web server, web browser, console interface, and terminal. Likewise, the interactor is fairly straightforward in terms of its translation to just administrator. Now, we don't know that this is an administrator. They're just an external user, but for the purposes of this example, we'll call them an administrator. One of the first things of note is the translation of our data stores. Because we have only one DFD symbol that we use for all resources, there's an adornment on that symbol that shows at a very high level whether we're dealing with structured or unstructured data. Specifically, the file icon versus the database icon that we're using here, which in the block view was very obvious as to the distinction. And we're going to use those here in order to make that more clear. It's important to note that your DFD creation utility may not be able to put this information there. And so an alternative would be to have some textual notation that you add to the diagram, because free text tends to be allowed in just about every system. There are two boundaries, and those are the core service boundary and the machine boundary. The directions of the arc show us that the most important thing in this element is the core service on this level. This diagram doesn't show a boundary between the resources and the processes. This is a simplification, and the reason for it is that there's an implicit trust between the core service, the console interface, and their respective resources, data stores in this case. So we don't bother putting that there. As mentioned, having unique process and resource names gives us the ability to have data flows which are also uniquely named when we're using the convention of source to destination. We don't have a callout here for the protocol that's being used between the web browser and web server, because in this case, only a single protocol is being used between them. We recognize additionally that this can't be all that there is within the actual system. We don't just have free-floating processes without some kind of operating environment which provides us the structures that we need in order to make connections between things like the resources and the processes in the outside world. So let's expand on this. To do so, we need to create another DFD that adds in the entities that have been left out. In this case, we can see that we're interfacing to the file system. So we're going to add the file system process, both for the core services configuration data as well as the console interface configuration data. Similarly, the core services data and the console interface data are both databases. So we're going to add a database manager. Communication between the core service and console interface, and between the core service and the web server, is accomplished via interprocess communication. And so we're going to add an interprocess communication manager. We know that the web server is going across the network to get out to the web browser, and so we're going to add the network manager. Finally, terminal communication is achieved via a serial driver, and so we add that in. Now that takes care of the processes, but we've now introduced another set of boundaries. We have the operating system boundaries between the web browser, core service, and console interface, and the interprocess communications manager and file system. And we have a boundary between the database manager and the core service and console interface. Within this system, a single database manager is being used for all the databases being managed. Note that this does not tell us anything about whether the databases shown are separate files or merely tables within a single database. None of that is relevant at this level. We've dropped the core service boundary, as the OS boundary is more significant. And we have a whole series of new data flows. And since we have decent process naming, we have unique data flows between the various entities. You'll note that there is replication of process entities for both the database manager and operating system processes. The reason for doing it this way instead of having one process entity with data flows going off in all directions is that it's difficult for a person to reason on the diagram otherwise. From the standpoint of analysis, there's no particular advantage to one approach over the other. However, from the standpoint of being able to show what's happening end-to-end for a data flow, this type of duplication of process node is more useful. As we look at this diagram, even with these changes, we still haven't identified all the processes that need to be in place. So let's repeat this exercise. Here's the level 3 DFD. The introduction of the database and the network managers exposes the need for additional interfacing processes. The database manager needs to access the file system in order to get to the database, and so we've inserted the file system and also an operating system boundary. Likewise, the network manager doesn't directly connect to the network. It requires a network driver. The reason we don't need a boundary between the network manager and the network driver is that both are owned by the operating system. The database, on the other hand, is not, which is why we have a database boundary rather than an OS boundary here. Just by having the boundaries, we can make certain inferences about the processes themselves. We'll address how to make that more obvious in a bit. An important thing to note here is just as with the operating system having its process nodes replicated, the same is done for the database manager nodes. Likewise, the boundaries all have unique names, which means that if you see a boundary in one section labeled OS boundary, and also in another section, then you know that if we were to create an unfolded form of the DFD, that the boundary would be contiguous. However, there's no motivation for us to do that, as it would only complicate the diagram. As it stands, this diagram is still comprehensible from the standpoint of the information that we got from development. As you can see, we still have these colored regions, which we took from the system diagram, and all the entities are logically placed within the context of each of these. Now let's look at how we're going to go about taking this information and documenting it. Now, it's not the case that you can just take your 3 levels of DFD, and you do need all 3 of them, and call it a day. As a side note, your actual system may require more or fewer of these base DFDs. You do need all of these diagrams, but they are insufficient for the purposes of threat modeling, and we'll address that later. The tools that you're using to create these DFDs could be anything that's out there that's available and able to give you this representational form. But there's additional information we need to capture. We're going to cover that next. The remainder of this presentation is going to be based on the least common denominator of tooling. We're going to use an Excel workbook with multiple sheets to capture the various pieces of information. If you happen to be using a tool that allows you to capture the same type of information, that's fine. This information will be carried into the analysis activity, so you should be able to see, as we evolve the material, why these choices were made. So back to the level 1 DFD. We're going to apply IDs to everything. We have 5 entity types. They are resources, processes, interactors, boundaries, and data flows. For the purposes of this example, we're going to use the following ID prefixes: ESR, example system resource; ESP, example system process; ESI, example system interactor; ESB, example system boundary; and ESD, example system data flow. This is purely for convenience. If you use a tool such as the Microsoft Threat Modeling tool, every entity is going to be assigned a GUID. However, it does have the drawback of being fairly opaque when it comes to human comprehensibility. So, for the sake of being able to show this in a way that makes it easier for a person to look at it, we're going to use the unique identifier prefixes as mentioned. As you can see, each data flow, process, boundary, interactor, and resource has been given a unique identifier. There's no necessity to put them in any particular order or to have them be sequential. Similarly, with level 2, we have more processes and an additional boundary that we need to include. And by the time we finish IDing all the level 3 entities, we're up to a fairly good number of entities that we need to keep track of. Here is the initial set of entities for this exercise. There's a template provided with the AVCDL material, and a link to it should be attached to the presentation's description. There are individual sheets for each of the different entity types: resources, interactors, boundaries, processes, and data flows. The first few columns of which are shown here. You have the ID, name, and description field. If you're using the recommended naming convention for data flows, it's not really required to put in a description because the name tells you that it's going from the source to a destination, whereas for processes, names may not be sufficient to convey what they are. Here's the DFD entity attributes diagram and attribute lists from the threat modeling overview video. We'll get into the specifics for each of these, what the attributes are, and why we care about them. For our purposes, we'll consider resources as data at rest. This is a fairly gross simplification because a resource could be an external data source. However, from the perspective of the DFD and the threat model, we look at it as if the resource is a static object. Now, within the space of the cybersecurity requirements taxonomy, resources are in the at-rest group of assets. There are 6 buckets for resources: executables, configuration data, unstructured data, databases, credentials, and logs. These in and of themselves are artificial divisions, but what they represent are specific entities that we wish to be able to make various cybersecurity property assertions about and establish requirements for. Within the context of threat modeling, we have the following attributes. If the resource has a unique ID, then there's some mechanism that will allow us to know that this resource is the resource that we want. This is most important when you're dealing with executables. The reason for that is that if you only use a mechanism such as the file name to identify an executable, then there's nothing preventing another file from being named the same. The problem from a cybersecurity standpoint is that we have issues of file paths being a chunk of metadata that tells us where to look for these things. And if all we do is look at the file and don't care about the path, this leaves us open to a whole host of issues. Next, we have whether the resource is logically read-only. For something like an analog data stream, well, obviously it's a read-only entity. If, however, we're dealing with base configuration information or other information which has no need for write access, then we want to be able to assert that it is read-only as a layer of protection. Whether or not the resource is structured is important because that informs us as to whether or not we're dealing with a database. It's important to know whether or not a resource contains PII or credentials. Both are important and significant. We deal with them separately, but fundamentally, they're characteristics of the data within the data store. Whether or not the data is encrypted. Note that the mechanism of encryption is not specified here. We only need to know that this layer of protection is present. Whether the data is integrity checked. Integrity checking both establishes that the data has not been tampered with, but also that it hasn't been corrupted accidentally. Finally, the resource type is identified. It can be analog, something not subject to cybersecurity consideration. It can be an executable. This covers all executables, and it doesn't matter whether we're dealing with drivers, services, or application binaries. There's no distinction between a compiled executable, interpreted code, or something that exists as firmware or microcode. These are sets of instructions which a processor uses in order to perform operations on data. Another type we have is configuration data, which represents metadata used to establish the behavior of the process. The final two types are logs. One is data, one is audit. There's an important distinction there. Data logs are generic information collected for the purposes of the system itself. Audit logs are there for the purposes of tracking specific system state changes, which are, in the case of cybersecurity, relevant cybersecurity events that occur in the operation of the system. In the case of our example, what we have is a set of 4 resources, 2 pair, 2 for core services, and 2 for console interface. One of each is a flat file that represents our configuration data. The other is a database, which is our live data. As we can see from the tabular form of the data, some of the information that we record is fairly obvious from the DFD itself. And that's great. If certain data can be derived, for instance, whether it's read-only, whether it's structured, the resource type, then feel free to pre-fill these things before getting into the question and answer with the development SME. Keep in mind that there are things that are going to require their input, and I don't know should not be an unexpected response. Remember that guessing is never an option when you're doing this type of cybersecurity analysis. If you can't assert that something is the case, then it probably isn't. If you don't know whether something is encrypted, don't presume that it is. Things will need to be verified, and there needs to be a positive assertion that something is the case. For process attributes, the applicable area in the requirements taxonomy space is within the at-rest assets, specifically executables. Now, obviously, when they're being executed, they're not at rest. However, they don't represent the externalizable data. What we have here is a particular bucket that we're looking at, and what we care about are the cybersecurity properties that are applicable to it. Within the context of threat modeling, we're going to care about whether it has a unique ID. We've already covered unique IDs within the context of resources. Within the context of executables, we care about these as they're running, as opposed to when we're looking at them as a resource. So we need some means that we can use to uniquely identify the process. There are a pair of attributes that we have that indicate whether the process is authenticated and authorized. Authenticated being that it is who it says it is. So we look at the process and we say, yes, this process is a valid process that's recognized. Second, that the process has authorization to perform the operation it's attempting. On some systems, these authorizations are known as entitlements. For instance, you may have a process that is responsible solely for managing a resource. That process should not be authorized to access the network. There's no necessity for it to have that type of capability. There are three types of processes. First are drivers. These are the lowest level process. They're typically in the kernel space and are responsible for interfacing to some chunk of reality. These are things like serial drivers, network drivers, disk drivers, things of that nature. Second, we have services. These are special processes which sit within the running system. They tend to be at a higher level of execution than normal processes, and they do things that are outside the scope of an individual normal user space executable. For instance, the printer or database manager could be considered a service. It just kind of sits there, it waits, you talk to it, and things happen. It tends to have specialized interfaces in order to communicate with it. Lastly, we have normal user mode processes. In addition to the type of processes, we have three process classes. One is the operating system processes. I'm not going to go and make any distinction between the elements of the operating system, whether that be the kernel itself versus operating system utilities that sit on top of it, or services or drivers or whatever have you. This is an ownership and a trust concept. Next, we have third-party processes. This is the class of all processes not owned by us or the operating system. So it could be open source, it could be a supplier component, it's not relevant, it's just at a lower trust level than ourselves. Next, we have self. This is basically everything we own. Finally, we have external. These are processes outside the element which it's communicating with. Now, you could create finer granularity here, but for practical purposes, this is going to be sufficient within the context of threat modeling. If we consider our example and focus on the processes, we can see that there are 11 of them. The process types are fairly obvious from the DFD. For the remainder of the attributes, we're going to have to ask questions, but we can make a couple of assertions. One is that the operating system's processes are going to be considered authorized and authenticated, and that their process class is OS. Another is that the elements processes are considered to be authorized and authenticated within the context of their intended use. As for the other attributes, we need more information. It's important to note that it's not always the case that we'll get the data right. So don't consider the threat model to be a read-only document. It's going to be revised at some point. Additionally, when you're dealing with external entities, treat them as if they don't have unique IDs. Since they're external to the system, there's no control over these things, and they may or may not be authorized or authenticated. For interactors, we only have a type. If it's a person, Well, we know what people are. We have certain expectations. For instance, there should be interfaces that front-end them. Otherwise, what we have is analog data that we're going to be doing an A to D conversion on. And there's no cybersecurity controls that can be applied here. The responsibility lies with the functional code to ensure that the data is reasonable. Our example system has one interactor. It's an administrator. As noted before, this could be labeled as user, but it's labeled as administrator, and the type is person. Having different types of boundaries is useful from the standpoint of threat modeling, but not necessarily in the context of the DFD. This is because we capture this information within the processes and data flows. We add this attribute because it helps us reason on the DFD non-programmatically. Let's consider the boundary types. Machine boundaries exist between the elements hardware and the outside world. Network boundaries exist between processes using networking as a communications mechanism. Interprocess boundaries exist between processes using operating system-mediated process-to-process communication. Operating system boundaries exist between operating system processes and other entities. Resource boundaries exist between a process and a resource it manages. External interactor boundaries are fairly arbitrary. One could argue that you don't have an external interaction unless you're processing a machine boundary. The same could be argued for networking, but it's not necessarily the case. You could use networking between processes even though interprocess communication may exist within the same machine. Within our example, we have 4 boundaries. The core services boundary, which is an interprocess boundary. We have the machine boundary between our element and the outside world. We subsumed the network boundary here for the purposes of convenience because we also have serial in addition to networked communication. And so we put a machine boundary there because it serves the same purpose. We have an operating system boundary between the core service and the file system, and also the core service and the interprocess communication system. Finally, we have an interprocess boundary between the elements processes and Database Manager. Finally, we have data flows. Arguably, these are the most important because this is where most of the action occurs. In our cybersecurity requirements taxonomy space, this is the data in motion asset region with the requirements at the network and protocol layers. The attributes are related to the cybersecurity properties. The first attribute for consideration is whether the data flow requires an acknowledgement. Although this may seem trivial, it's important to properly manage protocoled communication. Failing to consider requirement acknowledgement can lead you into all sorts of issues. Next, we have sequence numbers. This is not an issue for standard protocols because they all use sequence numbers for managing out of order and duplicate messages. It is a concern with custom protocols since it leaves the system open to a host of attacks. This is a design deficiency which can become fairly important as things scale. The next pair we have is authenticated source and destination. These are foundational to secure communications. Next we have whether or not it's safety critical. Safety criticality is not the only thing that we have here to consider. We could also say that this is cybersecurity critical. However, we tend to think about things which are safety critical as being the highest level of import when it comes to the controls that we have to put in place. Next is the integrity check, which has 3 options. The first is no check. The second is a simple integrity check, such as a CRC. And the third is a cryptographic integrity check. Finally is encryption, which also has three options. The first option is no encryption. The second is symmetric encryption. And last is asymmetric encryption. Obviously, protocols that are running on data flows can be layered, and one must consider each of these layers separately. If you have data flows between two processes that exist at different layers, you need to show them separately in order to reason on them appropriately. As one might expect, in our example, data flows represent the majority of items. Not called out as an attribute is a protocol associated with every data flow. Here we have function calls, IPC, HTTP, and HCI, human-computer interface. And then we have a whole host of attributes that are shown here. You'll note that there are blanks. This is information that we were not able to get. Data flows is where this is probably going to occur the most. In the next set, we have items 28 through 54, and looking at items 39 and 40, we can see that we have the browser to network manager and network manager to browser, which have TCP flows running below the HTTP flows. This is the case described earlier where you have different protocols with different mechanisms that you need to account for. Our last protocol here is serial I/O. Now, the template does not provide a set of protocols to choose from because it's impossible to know what they all are. And so they're just left to the cybersecurity SME to enumerate these. One might think that by the time we get to something like a level 3 DFD, that we're pretty much done, especially once we filled in all the various attributes for things. But actually, this is not the case. From the standpoint of threat modeling, what we've done is collected all the data. However, that data is not organized in a way which makes it easy for us to do any analysis. Yes, we could look at the entity-to-entity flows, but as has been shown, there's no way to talk about a particular end-to-end workflow. All we've done is create diagrams that show everything in the element and how it's connected. We haven't contextualized it, and that's what we're going to do next. And we're going to start with the OS-centric DFDs. So starting with the file system component of the operating system, we're going to show all of the touch points that the system has with it. This does two things. One is it gives us a base to be able to look at the cybersecurity controls which may not be within the context of the threat modeling that we're doing, but are appropriate to the implementation. This allows us to reason on those and say, yes, we've got these various controls in place. The other thing is that it allows us to double check that we haven't missed anything that we're going to need in order to be able to reason on the element. You'll notice that the diagram is fairly straightforward, and we can reason on it directly. Obviously, since this is the file system that we're talking about, this is a highly trusted component, and so all communications going through these data flows is trusted. A minor note, this DFD shows our color coding for levels of trust, green being the operating system, blue being ourselves, yellow being third party, and red being external. And the external piece is not shown in this particular diagram. The next component within the operating system we'll consider is the Interprocess Communications Manager. Here we have the core service, console interface, and the web server communicating with the Interprocess Communications Manager. We have the serial driver, and you'll note on the left the console interface in blue and the terminal in red, indicating that it is external to the system. Note that we're not using any boundaries here because the color coding does that indication for us. With the network manager, we only have the web server talking to it. Note that we're not showing the network driver on the other side because it's also an operating system component. We don't care about operating system to operating system components from the standpoint of our analysis of the element. Finally, we have the network driver component, and it's talking to the web browser. It's worth noting that in some operating systems, the network manager and driver may be combined. With this, we've covered all of the portions of the most trusted part of the system in the context of our element. We can look at these and place controls and then not have to worry about that layer within the context of the analysis that we're going to be doing on the element itself. The next set of DFDs to look at are those related to networking as a whole. This is especially important because so much of what is done within a system deals with communication between various elements and systems which rely on the network stack. It's also one of those areas where people don't give sufficient attention, and so it's worthwhile to take some time to diagram it specifically. In the case of our example, we only have one network path that we go through that connects the web server and the web browser. It traverses both the network manager and eventually the network driver. We're showing not only the trust levels, but also the boundaries here for emphasis. The final and arguably most important set of DFDs we're going to look at are the workflows. These are the operational flows that occur within the element itself. These are the ones of primary interest because issues discovered in threat modeling need to be mitigated. And if you give a person who needs to do this huge diagrams containing a ton of superfluous information, it makes it that much more difficult to perform the mitigation. And so these diagrams are small by intent. If an overly complicated DFD is needed to represent a workflow, this is a good indication that the workflow itself is overly complex and should be simplified. Our first workflow is the initialization of the core service. It's a fairly trivial one where we have the core service itself and its two data sources. Note that there's a block of text that provides a little bit of elaboration. This is within the DFD file itself. The reason for this is that it allows us to have information which makes it easier to interpret what the DFD is doing in certain situations. It's not mandatory, and yes, you could have references to external documents that contain this information, but where it's lightweight, there's no reason not to include it. Our second workflow is similar to the first, and this time it's for the console interface. In our third workflow, we're showing how the console interface is used to configure the core service. And finally, we show normal operation. This is a perfect example of how little we require in order to convey a particular workflow. We've seen how to translate a block diagram of the element into a series of DFD views. We've covered what the attributes of each DFD entity type are and how they're motivated. We've worked through a realistic example system. We've motivated why having a series of simple targeted views is superior to a big bang DFD. That covers the basics of how you would create a DFD-based threat model. This is not to say that all questions could possibly be answered from this material. However, the material provided should cover most things. The materials that were used to cover this example can be found in the locations shown here. It's important to note that this includes the DFDs, as well as the threat model, and the model creation workbook that goes along with it. All AVCDL materials, both in source and distribution form, are available on our GitHub site, as shown here. Because of the size of the repository, it's recommended that you either clone the repository or download a zip archive of it if you're not familiar with using Git. Instructions for downloading a zip archive are linked to on the repository's front page. A set of training videos have been created to cover various aspects of the AVCDL that follow the training path found in the AVCDL primary document. It's important to note that all AVCDL materials, except for the introductory blog posts, are intended for product cybersecurity engineering practitioners. The next step in the threat modeling sequence are the threat model analysis and threat candidate triage trainings. Once you've completed all trainings related to threat modeling, you can proceed to one of the other trainings at this level. These include attack surface analysis, penetration testing, and vulnerability identification. Additionally, if you've completed secure coding and its prerequisites, you can proceed to static analysis, dynamic analysis, fuzz testing, and source code review. Here are the references to the source material used in the creation of this presentation. They'll also be included in the video description. Additionally, this presentation source material will be provided on the AVCDL GitHub repository.